Hi, in this video, we are going to look at a few problems in number theory. We are going to apply the concepts that we have learned so far in the course. So I'm going to discuss 5 problems. You should attempt the problems yourself before you look at the solution. So what you should do is, when I state the problem, you should pause the video and try it yourself and then look at the solution. So let's start off with the first one. The first question says, let m and n be integers such that GCD of m and n plus LCM of m and n is equal to m plus n. We have to show that one of the two numbers is divisible by the other. Okay, so this is a pretty easy problem. We can start by saying let's call G as the GCD of m and n. And now we know there is an identity that GCD times LCM is equal to product of the two numbers. So therefore we have G times LCM of m and n must be equal to m and n. So therefore we can say LCM of m and n is equal to mn divided by G, right? And now using the identity stated in the problem, we get G plus mn by G is equal to m plus n. Now simplifying this, you get G square plus mn is equal to m plus n times G. Bringing it to one side, we can easily factorize it. G square minus m plus n times G plus mn equal to 0, which means G minus m and G minus n equal to 0. So that implies that G should be either m or n. And G was the GCD of m and n. So if the GCD of two numbers is one of the numbers, then it is obvious that one of the two numbers is divisible by the other. Basically, we are saying if G is equal to m, then m divides n, because G divides n, right? And vice versa. So this is a pretty straightforward question. We wanted to start with an easy one. Let's go on to the next problem. This is from Iran 2005, the Maths Olympiad in Iran. So let's look at this one. Let n and p be greater than 1 and be positive integers. And p is a prime. Given that n divides p minus 1 and p divides n cube minus 1, we have to prove that 4p minus 3 is a perfect square. Right. So we have this information, n divides p minus 1 and p divides n cube minus 1, where n and p are greater than 1, they are positive integers, and also p is a prime. We have to show that 4p minus 3 is a perfect square. You should pause the video at this point and try the questions yourself. I will go ahead with the solution. So let's try to analyze what we can deduce from here. So we have n divides p minus 1. So that implies that n must be less than equal to p minus 1, because n must be smaller so that it can divide it, right? So that implies that p is greater than equal to n plus 1. This is the first thing that we get, right? Also from here we can say p minus 1 should be equal to some integer k times n, right? Because n divides p minus 1, p minus 1 is k times n. So we get from here p is equal to n times k plus 1, where k is any integer, right? So these are the two conclusions that we have gotten from the first statement, that n divides p minus 1. Now let's look at the other statement. P divides n cube minus 1, and n cube minus 1 can be written as a factor n minus 1 times n square plus n plus 1. So we have P divides the product of these two things. Now you should realize that P cannot divide n minus 1. P cannot divide n minus 1 because we have already seen that n divides P minus 1, right? So that means P is greater than n plus 1, we already know. If P is greater than n plus 1, it cannot divide n minus 1 because it's a smaller, right? So P does not divide n minus 1. And since P is a prime, you can also say that P does not have any other factors. So none of the factors of n minus 1 are factors of P, right? Because P is a prime. So a prime number, basically you are saying something like this. If P divides A times B and P does not divide A, then that means P divides B, right? I hope you understand what I'm saying. P divides the product of two numbers and P does not divide A. That means P divides B. So from here, we know that P does not divide n minus 1. So that implies P divides n square plus n plus 1, right? So we know that P divides n square plus n plus 1, which implies P is less than equal to n square plus n plus 1, right? Okay. So what was P? We can use P is nk plus 1. So we have nk plus 1 divides n square plus n plus 1. Here we are using the fact that P had come as nk plus 1 earlier, right? So we have nk plus 1 divides n square plus n plus 1. And now we will continue on the next screen. We have this result. Nk plus 1 divides n square plus n plus 1. So obviously nk plus 1 should also divide k times n square plus n plus 1, right? That is obvious. That is not an issue. And we can also say that nk plus 1 therefore will divide k times n square plus n plus 1 minus n times nk plus 1. Since nk plus 1 divides this, and clearly nk plus 1 divides this, so the difference of two numbers, this and this, is also divisible by nk plus 1, right? The reason we did this subtraction is because now we'll be able to cancel the nk square. So this term will become kn square plus kn plus 1 minus kn square minus n, right? So kn square will get cancelled and you'll have kn minus n plus 1, right? Not kn. We have kn plus k here. Kn square plus kn plus k. So we have kn plus minus n plus k. So what we are concluding is nk plus 1 divides kn plus k minus n, right? Great. So that means that nk plus 1 is less than equal to kn plus k minus n. And now we can cancel off the kn from both sides of the inequality. And we got n plus 1 is less than equal to k from here, right? Now think about earlier what we had seen. P was equal to nk plus 1, and we had already established that it was greater than n plus 1, right? So nk plus 1 was greater than n plus 1 we had here, right? And we know that k is greater than n plus 1, right? So nk plus 1 is greater than equal to n times n plus 1 plus 1. Actually, we don't need this part of the inequality. We'll just say nk plus 1 is equal to p and k is greater than n plus 1. So this is greater than this. So we get p is greater than equal to n square plus n plus 1 from here, right? So remember earlier we had said that p divides n square plus n plus 1, right? We know this from here. P was this, P divides this. So we have P is less than equal to n square plus n plus 1. And now we have concluded that P is greater than equal to n square plus n plus 1. So that means Both the things can be true only if actually what we have is p is equal to n square plus n plus 1, right? So if p is equal to n square plus n plus 1, that is our conclusion, then 4p minus 3 is equal to 4n square plus 4n plus 4 minus 3, which is equal to 4n square plus 4n plus 1, which is equal to 2n plus 1 whole square. And therefore 4p minus 3 is a perfect square. So we have come to the end of the proof. However, keep in mind what ideas we have used in this. We use the fact that if p divides n, it implies p is less than equal to n, this idea. I should write p divides n. This idea we have used repeatedly here. Then the other idea we used was p divides AB and p does not divide A, implies p divides B. We use this idea. And finally, we use the fact that if p divides n, which implies p is less than equal to n, and we can get that p is greater than equal to n also by some other way, then that implies that p equal to n, right? So these are the basic ideas that we have used here. And you can go through the steps once more and you will realize that it works, right? So that is our solution for this particular question. Now we move on to the next one. Question number 3. This is an APMO question, Asia Pacific Maths Olympiad. Okay, so the question is, are there distinct prime numbers A, B, and C such that A divides BC plus B plus C, B divides CA plus C plus A, and C divides AB plus A plus B. So that is the question. Is it possible that there are three prime numbers A, B, and C such that these three things are happening, right? So let's analyze one of them because it is very symmetrical. So if we analyze one of the things, you can make conclusions about the others also. So what is BC plus B plus C? It can be easily written as BC plus B plus C plus 1 minus 1, which becomes B plus 1, C plus 1 minus 1, right? So we have A divides B plus 1, C plus 1 minus 1, right? Now it is still this expression is still not perfectly symmetric. It would have been perfectly symmetric if I had a factor of A plus 1 here also, right? So what I will do is just multiply. Since A divides this, A will also divide A plus 1 times B plus 1 times C plus 1 minus A plus 1, right? We have just taken A plus 1 and multiplied it on the right hand side. Obviously, if A divides this, it will divide a product of this into A plus 1, right? So this is a correct statement. And now from here, what we can conclude is A divides A plus 1, B plus 1, C plus 1, minus A minus 1. So obviously, if I add A to the right hand side, it will still be divisible by A, right? Because A itself is divisible by A. So I will just add plus A to this, which implies A divides A plus 1, B plus 1, C plus 1, minus 1. I have added plus A to this thing because if A divides this thing, then it will also divide plus A, this thing plus A, right? So we are getting this result. Now it is perfectly symmetrical. So we have gone from here, we have reached here, right? So obviously we will have similar inequalities here as well. B will also divide this, C will also divide this, right? Because it's perfectly symmetrical. So we have these conditions now. A divides A plus 1, B plus 1, C plus 1, minus 1. B divides A plus 1, B plus 1, C plus 1, minus 1. And C divides A plus 1, B plus 1, C plus 1, minus 1. these three results we have, and you should realize that ABC are prime numbers. ABC are primes. So LCM of ABC will be simply A times B prime C. They have no common factors. So LCM is the product. And A and B and C, all of them divide this thing, right? So we can say, therefore, A times B times C will divide A plus 1, B plus 1, C plus 1, minus 1, right? So because we have ABC will also divide this, you can now conclude from here that ABC will also divide A plus 1, B plus 1, C plus 1, minus 1, minus ABC, right? And this simplifies out to be AB plus BC plus CA plus A plus B plus C. So we have ABC divides AB plus BC plus CA plus A plus B plus C. From this, we can say, we can divide by ABC on both sides, and we can say, or we can make an inequality like this: ABC is less than AB plus BC plus CA plus A plus B plus C, which implies 1 is less than 1 by A plus 1 by B plus 1 by C plus 1 by AB plus 1 by BC plus 1 by CA, right? This is what we have concluded, right? This inequality. Let's work on this on the next screen. So we have 1 is less than 1 by AB plus 1 by BC plus 1 by CA plus 1 by A plus 1 by B plus 1 by C. And for the primes A, B, C, we can assume without loss of generality that A is greater than B is greater than C, which implies 1 by A is less than 1 by B is less than 1 by C, right? Correct. So if we assume that, or actually we'll assume the opposite. We'll assume 1 by A is less than B is less than C. Let's assume it like that. That is the same thing. 1 by A is greater than 1 by B is greater than 1 by C now, right? So that means that this expression, if I replace 1 by B as 1 by C, all the 1 by B's and 1 by A C's as 1 by A's, I can write 1 is less than equal to, we know that 1 by A is the biggest out of these, right? So I'm replacing 1 by B with 1 by A. So less than equal to 1 by A square plus 1 by A square plus 1 by A square plus 1 by A plus 1 by A plus 1 by A. What I'm saying is this expression is less than this because we have assumed that 1 over A is greater than 1 over B is greater than 1 over C, right? So we are getting 1 is less than equal to 3 by A square plus 3 by A, or we are getting a quadratic like this: A square minus 3A minus 3 is less than equal to 0, which implies by the theory of quadratic functions, A must lie between the roots. One of the roots is negative, the other root is greater than 3. This root will be 3.75 or something. So we get from here that A is less than equal to 3. Now, because A was supposed to be a prime number, we have two cases. A can be 2 or A can be 3, right? These two cases are coming. Now we work with each cases and do case work. So what do we have here? We have A is less than B is less than C. We have A can be 2. This is case 1 for us, right? So if A is 2, let's look at the original inequality. We have 1 by 2B plus 1 by 2C plus 1 by BC plus 1 by B plus 1 by C plus 1 by 2, right? So simplifying this, this becomes half is less than equal to 3 times B plus C plus 2 by 2BC, and which further simplifies as BC is less than equal to 3 times B plus C plus 2, and you can, after a little bit of calculations, you can simplify this like this: B minus 3, C minus 3 is less than equal to 11, right? If b minus 3 and c minus 3 are less than equal to 11 and b and c are primes, where a has been taken as 2, b, c could be anything from 3, 5, 7, 11. These are the primes, right? That b and c could be. Because b has to be greater than a and c has to be greater than b, right? So you can check these conditions. So you can take, if you take b as 3, c could be anything, right? B minus 3, C minus 3 has to be less than 11. If you take B as 3, C could be 5. In that case, this inequality is satisfied. However, now you have to check the original inequality. So you have to check A is equal to 2, B is equal to 3, C is equal to 5. Does it work for the original inequality, right? So what was the original inequality? You had A divides A plus 1, B plus 1, C plus 1 minus 1, and similarly B, C. So let's calculate A plus 1, B plus 1, C plus 1 here. It is 3 times B plus 1 is 4 and C plus 1 is 6. So 71. So 71 is a prime. So 2 does not divide 71. So 3 does not divide 71. So basically this doesn't work. This case doesn't work. So that means B cannot be 3. If you take B as 5, C must be 7 or 11 or something like that, right? So if B is 5 and C is 7, we have 2 into 4, 8. This inequality is satisfied. And again, you will check whether it works or not. A is equal to 2, B is equal to 5, C is equal to 7, whether it works or not here. So you will get 3 times 6 times 8 minus 1. So that is 24 into 6, 144, 143. So 2 does not divide 143. So this is also not working, right? So basically, you have only a limited cases that you can check. Now, we have seen that B is 5 and C is 7 also doesn't work. If you take B is 7 and C must be 11 then. Now this inequality will not work because you will have 7 minus 3, 4 and C minus 3, 8. 32 is not less than 11. So there are no cases for which this inequality is true and the original statement is true, especially when the case was A is equal to 2. Similarly, you have to do the other case also where you take A is equal to 3. And if A is equal to 3, again you will say that A is equal to 3 is less than B is less than C. So B and C can start from 5 and 7 and so on, right? And these must be prime numbers. You do the casework again there, you will realize that you will not be able to satisfy the conditions of the problem. So I will leave that second part of the problem to you. So you work it out and see if you're getting the cases, and you should be able to prove that no such A and B and C exist, right? Let's move on to the next problem. This is the fourth one. This question says, show that for all primes, for all prime numbers P, Q of P, which is equal to product of K goes from 1 to P minus 1, K power 2K minus P minus 1, is an integer. Okay. So this is a product. So first we have to try to simplify the product in a nice way. So let's think about it. Product of K goes from 1 to P minus 1. And we can write this as K power K whole squared by K power P plus 1, right? Okay. So K power K whole square becomes, since it's a product, we take K as 1. So it is 1 power 1, 2 power 2, 3 power 3, and so on till P minus 1 power P minus 1 whole square on top, divided by, this is 1 into 2 into 3 till P minus 1 and whole thing to the power P plus 1, right? So let's figure out the numerator first, because the denominator is simple. Denominator is simply P minus 1 factorial to the power P plus 1. right? So let's figure out the numerator part first. So notice that this is 1 square, 2 square, 3 cube. So the number of 2's is 2, number of 3's is 3, and so on. So we can write it as 1 into 2 into 3 till p minus 1 multiplied by, see, 1 has come only once, so 1 can be written only once, right? Now 2 has come twice, so we can write it as 2 into 3 into till p minus 1. 2 has come twice. Now there will be no more 2's. Now there will be 3 into 4 into till p minus 1. Notice that p minus 1 comes p minus 1 times in this factor, right? Correct. So I am just trying to simplify what is inside and I am writing it like this. 4 into 5 into p minus 1. And finally there will be one which has only p minus 1, right? And the whole thing is squared, right? The whole thing is squared. So what is this? We have to understand that in this product, in this whole product, 1 comes once, 2 comes twice, 3 comes 3 times, 4 comes 4 times, and p minus 1 similarly comes p minus 1 times. So you should understand that this is an accurate way to write the numerator, right? And now think about it. This is what? This is p minus 1 factorial. This is p minus 1 factorial divided by 2 factorial, divided by 1 factorial. And this is p minus 1 factorial divided by 2 factorial, right? And similarly, the last one is p minus 1 factorial divided by p minus 2 factorial, right? So if I do this on the next screen, the numerator starts looking like this. P minus 1 factorial times p minus 1 factorial by 1 factorial, p minus 1 factorial by 2 factorial, till p minus 1 factorial by p minus 2 factorial and whole square, right? Great. Okay. So this is my numerator, and in the denominator we have p minus 1 factorial to the power p plus 1. This was my denominator, right? Okay. So now again we have to think of simplifying it. Notice that there are p minus 1 terms here. The number of these terms is p minus 1, right? So yeah, it goes from 0 to p minus 2 factorial. So p minus 1 terms, yeah. And what we can do is the top part can be combined and written like p minus 1 factorial to the power p minus 1 divided by 1 factorial, 2 factorial till p minus 2 factorial, and the whole thing is squared. And we have on the side 1 by p minus 1 factorial to the power p plus 1, right? Okay. So in order to get it to look more symmetrical, what we can do is p minus 1 factorial. This is 2p minus 2 here, power 2p minus 2. So I'll keep the 2p power on top and put the power 2 in the bottom. So I'll get 1 factorial, 2 factorial, p minus 2 factorial, and p minus 1 factorial whole square here. And outside here I have p minus 1 factorial to the power p plus 1. So the idea here is that this p minus 1 factorial to the power p plus 1 will cancel here, and it will become 2p minus p plus 1, right? So you will get finally p minus 1 factorial to the power. On top it becomes p minus 1 divided by, we have 1 factorial, 2 factorial till p minus 1 factorial whole square, right? Let's simplify that on the next screen. We have so far qp is equal to p minus 1 factorial to the power p minus 1 divided by 1 factorial, 2 factorial, till p minus 1 factorial whole square, right? So now it's about trying to arrange the things so that we can figure out something about the integer nature of q and q of p, right? So let's think about this. This thing can be written as p factorial divided by p to the power p minus 1, and the denominator is untouched, whole square. So why did I do this? Because I want a p power p minus 1 here, and here it is 1 factorial, 2 factorial till p minus 1 factorial whole square, and on top I have a p factorial power p minus 1, right? So now what I will do, notice that there are p minus 1 terms of p factorial here, and there are p minus 1 p's here, and I just need to use these somehow, right? So I can write it as p factorial divided by 1p and p factorial divided by p and 1 factorial and p minus 1 factorial. What have I taken? Notice what is this? This is 1 factorial, 2 factorial till p minus 1 factorial, and on one more pair of 1 factorial, 2 factorial till p minus 1 factorial, right? Now what am I doing here? I am writing this as one term. This is p factorial, 1 p factorial from here, 1 factorial from here, and 1 p minus 1 factorial from here, right? And 1 p from here. Then another term would be p factorial, one more, then 1 p here, and we have 2 factorial and p minus 2 factorial, right? And similarly, we'll keep making terms like this. This is 1 p by p factorial, and one more time we have p minus 1 factorial here and 1 factorial here. So think about what I have done. I have split this expression into multiple terms. How many terms? We have basically p minus 1 terms, right? Because that many p factorials we have, right? P minus 1 terms, and every time what am I doing? I'm taking 2 terms from here. 1 factorial, p minus 1 factorial. So I can take this and I can take this. 2 terms from here. The total number of terms here is 2p minus 2. Again, 2 terms here. 2 factorial and p minus 2 factorial from here. And I'm going on like this, right? And every bracket has a 1 by p from here, and there are p minus 1 p's here, right? So you should understand that this is working out perfectly. What was the reason for doing this? Because now we can write this as pc1 or 1 over p times pc2 1 over p, and so on 1 over p here, and this is pc1 as pcp minus 1, right? So q of p, after a lot of simplification, has turned out to be pck 1 over p product from k goes from 1 to p minus 1, right? This is my q over p. Now you can check that this is a very common identity, that pck is divisible by p, or pck is congruent to 0 mod p when k goes from 1 to p minus 1. You can check this identity. This is a true statement. You can check it with any prime number p and any integer k. Okay. So that means that this is an integer, right? And since this is an integer, q over p becomes a product of integers. We have done the simplification and we got q over p as product of pck by p, and pck is divisible by p. You can prove that yourself. And you will realize that Q over P is a product of integers, so must be an integer itself, right? So that concludes our proof. The main part of this proof was rearranging Q over P intelligently. A lot of effort went into that rearrangement, and hopefully you have understood the steps. You can try it out yourself and see that we have done the correct simplifications. Before we do the next problem, I would like to quickly talk about a simple idea. This is known as the four-number lemma. Four-number lemma. So this states that let A, B, C, D be positive integers such that AB is equal to CD. AB is equal to CD. We can show that there exist four positive integers PQRS, PQRS such that A is equal to PQ, B is equal to RS, C is equal to PS, and D is equal to QR. Now, this can be proved very easily. We can say AB is equal to CD means A over C is equal to D over B. And let's say that these two fractions are equal to some fraction Q over S, where this is in lowest terms. So GCD of Q and S is equal to 1, right? So then we can say that, okay, A over C is equal to Q over S. So A can be PQ and C can be PS, right? Where P is some integer, right? And similarly, D over B is equal to Q over S. So D can be QR and B can be RS, right? So we are getting this, that A must be PQ, C must be PS, and B must be RS and D must be QR, right? So this lemma we'll be using in this problem, the fifth problem. So this is a team selection test problem from India. So this is for the people who have qualified from Indian National Maths Olympiads and the questions that they practice with before the actual team selection. So the question is this: let A, B, C, D be pairwise distinct positive integers such that A by A plus B plus B by B plus C plus C by C plus D plus D by D plus A is an integer. Pairwise distinct means they are all different from each other. Any two of them are different from each other. We have this sum is an integer, and we have to prove that A plus B plus C plus D is not a prime. Is not a prime. Okay. So in order to approach this problem, we have to deal with this sum of fractions, right? Well, let's call it x is equal to A by A plus B plus B by B plus C plus C by C plus D plus D by D plus A. Now, by symmetry, if you have defined x like this, you can obviously define another y, which is B by B plus A plus C by C plus B plus D by C plus D plus A by A plus D, right? Because obviously here the denominator was A plus B and numerator was A. So we could have taken B and B, A plus B, C and C plus B, taking the other part of the denominator, right? The question has said that x is an integer. X belongs to integer. So we can check that x plus y. What is x plus y? When you add x plus y, what is coming? It is coming 1 plus 1 plus 1 plus 1. You can do it yourself. It is obvious. So x plus y is equal to 4. And therefore, x is an integer. Therefore, y is also an integer. Right? Since x is an integer, y is also an integer because x plus y is equal to 4, right? Now let's think about x a little more. X was a by a plus b plus b by b plus c plus c by c plus d plus d by d plus a, right? Also, a, b, c, d are all positive integers. So we can definitely say that a by a plus b is greater than a by a plus b plus c plus d, right? And similarly, this is greater than b by b plus c plus a plus d, and c by c plus d plus a plus b, and d by a plus b plus c plus d. So this is obvious because a, b, c, d are positive, so this inequality is true. And if you add these four, you will get 1. So we know that x is greater than 1. X is greater than 1, and similarly, you can also prove that y is greater than 1. And if x and y are greater than 1 and x plus y is equal to 4, then it is obvious that x is equal to y is equal to 2. There is no other option, right? So we have realized that x and y are both equal to 2. Therefore, x minus y must be equal to 0, right? So now what we will do is, because x minus y is equal to 0, we'll just simplify it. The next few steps are basically pure simplification of algebra. So we have x minus y, which is equal to a minus b by a plus b plus b minus c by b plus c plus c minus d by c plus d plus d minus a by d plus a must be equal to 0, right? So this is pure simplification. The only thing is you group the correct terms, you group this and group this and this, right? If you group this plus this, you do that calculation, you will get twice of AC minus BD by A plus B times C plus D plus twice of BD minus AC by B plus C, A plus D. This must be equal to 0. Now taking AC minus BD common twice of, you will get 1 over A plus B, C plus D minus 1 over B plus C, A plus D is equal to 0. And let's simplify this also. After simplifying, you will get 2 times AC minus BD, and on top what you get is A minus C, B minus D by A plus B, B plus C, C plus D, D plus A is equal to 0. I have skipped some steps where I just simplify the algebra, so you can try it out yourself. And since we know that A, B, C, D are all distinct, therefore A minus C and B minus D are not equal to 0. So this fraction cannot be 0. So that means AC is equal to BD. We have got that. Because of x is equal to y, we got AC is equal to BD. Now by the 4-number lemma, A must be equal to PQ, B must be equal to PR, C must be equal to RS, and D must be equal to QS. The 4-number lemma that we saw previously tells us that A and B and C and D can be written like this. So when you now take A plus B plus C plus D, you will realize it is PQ plus PR plus SR plus QS. So this can factorize as P plus S times Q plus R. So A plus B plus C plus D is coming out to be product of P plus S and Q plus R. Therefore, A plus B plus C plus D is not a prime, because it can be written as the product of two integers which are not equal to 1. So that's how basically we finished the problem. The idea was the 4-number lemma, and also the idea of when you have x, which was a sum of some fractions, we should also think of the symmetric part of it, which is y. If you built up your y as well, you could basically compare x and y and realize that both must be equal to 2. So please go through the steps where we did that comparison. We said that x plus y is 4, we said x is greater than 1. Similarly, y is greater than 1 by basic inequalities, and therefore x plus y is equal to 4 has only one possible solution, that x and y are both equal to 2, right? So hopefully you learned something from this video. We saw 5 problems, we saw 4-number lemma, and we'll continue with more lessons on number theory, more problem solving videos. So I'll see you next time. If you like the content, please like the video and share my channel with your friends. I would love to have your support for the channel and the content that I'm presenting. See you next time.